Good day, everyone. We're Team Misty. We are from Section EB1, and today my teammates Tan Zhengyu, Benjamin Chu Junjie, and I, Chu Ching, will present our Assignment 2 project. We are proposing a digital calibration management system with an adaptive measurement uncertainty calculator. Measurement is a crucial activity in engineering, manufacturing, and laboratories. We rely on instruments like vernier calipers, thermometer, and pressure gauge to obtain values for products and experiments. However, if these instruments are inaccurate, our measurement results become unreliable. This is why calibration is required to ensure accurate, consistent, and traceable results. Our proposed system helps users manage these calibration records and automatically calculate measurement uncertainty. It supports compliance with key standards such as ISO IEC 17025 for laboratory competence and ISO 10012 for measurement management. Currently, many calibration records are still managed manually using paper forms or spreadsheets. This often leads to calculation mistakes, missing history, and poor measurement traceability. Our primary problem statement is that manual calibration management reduces the reliability of measurement results. The main issues include human error during calculations, incomplete records, the absence of automatic uncertainty calculations, and the flawed practice of using the exact same formula for completely different instruments. Ultimately, this affects measurement accuracy, product quality, and standard compliance. To resolve these issues, our project aims to achieve 7 key objectives. We want to register and manage measuring instruments, record calibration readings digitally, automatically identify the instrument type, apply the suitable uncertainty components, calculate both error and uncertainty, determine the pass or fail status of the instrument, generate comprehensive calibration reports. Regarding our project scope, the system includes instrument registration, digital data input, additive uncertainty calculations, compliance checking, report generation, and database storage. We cover specific instruments: the vernier caliper, micrometer, thermometer, weighing scale, and pressure gauge. However, we exclude real hardware integrations, the physical calibration process itself, and official accreditation applications. Our system is built around major metrological standards. These include MS-ISO IEC 17025 for testing and calibration laboratories, JCGM 1002008 for evaluating measurement uncertainty, MS1 ISO 10012 for measurement management systems, and ISO IEC 25010 for software quality. Following these standards is vital. They ensure that measurement results are reliable, consistent, and acceptable for industrial use. They also provide a fixed procedure to reduce human error, guarantee proper measurement traceability, create better documentations, and ultimately result in higher user confidence. Our methodology is divided into 4 phases. Phase 1 is instrument identification, where the user registers the instrument with details like its ID, range, resolutions, and due date. Phase 2 is data input, where reference values are and measured readings are entered and saved into the database. Phase 3 handles uncertainty evaluation. The system calculates the mean reading, error, and all standard and expanded uncertainties to ensure proper metrology practice. Phase 4 is reporting. The system compares the result with the maximum permissible error to determine a pass or fail status and generates the final calibration report. This is the flow of our system. The process begins by registering or selecting an instrument and identifying its specific type. The system then branches out depending on whether it is a vernier caliper, thermometer, weighing scale, or pressure gauge. It loads specific uncertainty parameters. After the user enters the calibration data, the system calculates the mean reading, error, individual standard uncertainties, and combined uncertainties. It is then compares the expanded uncertainty with required tolerance to evaluate a pass or fail status. Finally, it generates the report, stores the record in database, and ends the process. This table highlights how our system dynamically adjusts its parameters. For instance, a micrometer accounts for resolution, repeatability, and the spindle effect. Meanwhile, a weighing scale evaluates resolution alongside drift and eccentricity. This ensures every instrument is evaluated accurately. So here are the core mathematical formulas our system executes automatically. The mean reading is simply the sum of readings divided by the number of readings. Measurement error is calculated as the measured value minus the reference value. We calculated the combined standard uncertainty using the root sum square methods, as shown here. So the expanded uncertainty is derived by multiplying the combined standard uncertainty by k, which is the coverage factor. Moving on, we outline the system's compliance procedure. This is divided into two main sections, the step-by-step compliance checking process and the vital calibration records we maintain. The compliance checking process follows a clear automated 9-step sequence. It begins with registering the instrument details and entering the reference and measured values. The system then automatically calculates the mean reading and measurement error. Crucially, in step 4, it identifies the correct uncertainty components based on the specific instrument type. It then computes type A, type B, combined standard, and expanded uncertainties. Finally, it compares these results against the tolerance or maximum permissible error to determine a definitive pass or fail status, culminating in the generation of a safe calibration report. To ensure full compliance and traceability, our system stores specific required calibration records. We log the instrument ID and type to track the correct tool and apply the appropriate uncertainty modules. The calibration date and next calibration date are recorded to verify the instrument's validity and prevent the use of expired tools. We also store the reference value, measure ratings, and measurement error to evaluate repeatability and deviation from accepted standards. Lastly, the comprehensive uncertainty results and the final pass or fail status are permanently recorded to prove whether the instrument is suitable for continued use.
Okay, hi Doctor. Today we would like to present our digital calibration management system. So this is our system. So consist of two pages. One is the instrument, where we can manage the calibration instrument here. Okay, and also we can see the calibration record and the uncertainty result based on the item. So we can view inside, so you can have the thing like this one. Okay, and also the instrument. It look like this. So okay, so now I will be showing how to add a new instrument. So for the research assistant to easily to record the instrument. So this is this, and I fill it. I already fill it out. So you can see if the instrument code name, and we can choose the type here. Because after that, the calculation will be different based on the type and the status. And write the brand, model, serial number, and all the items required to register instrument. So like this one, you already registered. You see the profile here. So easy for research assistant to know the instrument detail and also the recent calibration record. The recent calibration record will be conducted from time to time to ensure the calibration is correct. Okay. So let me start to the calibration. Okay, so this is the calibration section. You can see the reference value, tolerance, all the configuration here, and also the measurement data and uncertainty component entry here. So let me fill it out. So now I already record all the things. So I do all the things and reading. So all the things I've already filled out. If you want to add the reading, you can also add here. So let's the record. Okay, after set the record, you can see the result either it pass or fail. And it can have all the calculated mean reading, measurement error, standard uncertainty. So all the things are actually calculated based on the regulation. And it can also generate a printable report. Maybe like this one. Okay, so that's all for me. Thank you.
Hi, Doctor. To test our system, we proceed a test run using this instrument, a Bronner caliper, 150 mm. And here's the result we get from the system. We got the reference value, which is 25 mm, and the mean reading obtained from this 5 repeated reading. And so we compare with mean reading and reference value, we get the measurement error. And also we will obtain combined centered uncertainty as standard uncertainty in this system. And here's the tolerance of this specific device. And since it is lower than the tolerance, so the system will flag it as pass. So this device is considered calibrated. So this system successfully calculate all this result, and it also successfully determine whether the instrument is good to use or not. So the benefit of using this proposed system is we can definitely reduce manual calculation errors since it's automatically calculated by the system. And we can improve calibration record traceability. We can get all the reference value from this system. It's easily to access to them. And we can apply different uncertainty models based on the instrument type all recorded in the system. And we can produce consistent calibration reports. And it supports compliance with this stated standard and certification. So in conclusion, compared with paper forms or spreadsheet, this digital system provides a more structured and reliable method for calibration management. And the adaptive uncertainty calculator is important also because each instrument has different uncertainty contributor. To sum up this assignment, so the focus of our project is on supporting compliance with recognized standard and certification requirements in calibration and measurement management. And the standard we apply in this project included ISO, IEC 17025, GCGM 100 2028, ISO 10012, and ISO IEC 25010. So the system promotes reliable measurement result, proper uncertainty evaluation, and traceable calibration records. Consistent procedure and better documentation follow these applied standards. And the benefit of the system is it supports compliance through instrument registration, the record management, and the adaptive uncertainty calculation for different type of device. And also it can automatically checking pass or fail. And it also consider a consistent report generation. Overall, this project demonstrates how computing can be used to improve metrology practices and help organizations prepare for standard-based certification for calibration. That's all for the presentation of our assignment from Group Misty. Thank you, Doctor.